Algebra 2, Unit 6, Lesson 5, and in this lesson we're going to talk about the quadratic roots and the discriminant. And this is kind of a tie-on to what we did with the quadratic formula in the last lesson. We know that we can use the quadratic formula. If we have a quadratic equation, we can set it equal to 0, and then we can plug the a, b, and c values into the equation. And what I mean by the a, b, and c values is if we have f of x equals ax squared plus bx plus c. My a, b, and c values are the coefficients in front of each term. The c is the constant. It's very important that we understand this is the standard form of a quadratic equation. As we move forward in the course, we're going to learn how to rewrite this as vertex form. But for now, standard form is the form we have to have in order to use the quadratic formula. And then the quadratic formula, this is used to find the roots. It will work in any quadratic equation that I give you as long as it's in this form. And then we know that the roots, the place where they cross the x-axis, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in the last section, we did a whole bunch of different examples using this. And there were 4 specific types of examples that I want to talk to you about today. In these examples, this number underneath the radical sign tells us a lot about the roots of the quadratic equation. And as we move through this course, we're going to learn more and more about analyzing our graphs and what happens in those graphs. And some of the really significant information comes from the discriminant in a quadratic equation. And not only can we use this information in quadratic equations, but it also is very useful when we're dealing with any kind of polynomial function that we're graphing. So it's very important that we understand how the discriminant affects what we're graphing. So over here I have the 4 examples, or 4 of the examples that we did in the last section, the original problem and their roots, so that we can see what the roots were. And then we're going to talk specifically about the discriminant, what was underneath that square root when we plugged into the formula. So go ahead, copy these down, understand that these are the ones that we've already done. We did those in our notes in the last unit. And then copy down this chart. We're going to talk about 3 things: what the value of the discriminant is, what that means for the type and number of roots that the quadratic equation will have, and what the graph of that quadratic equation might look like. So go ahead, pause the video, copy this stuff down, and then we'll talk about it. Okay, so remember, the big thing here is the discriminant. The discriminant is the information that's underneath the radical sign in the quadratic formula. So in that formula, if you think about it, the stuff underneath the square root sign was the b squared minus 4ac. So whatever this number is underneath the radical becomes very important to our graph. So in this one, when I did this, my b squared, if I just do the discriminant, and in your work tonight, you're just going to find the discriminant. You don't have to even find the roots. We're just going to talk about the discriminant, what that number is, and how it affects the graph. So in the discriminant, b squared was 144. And then the minus 4 times 1 times negative 28. And then the number underneath that radical sign, ended up being 256. So now, all we need to worry about is what this number is, because that's what's significant about what happens with our roots. Well, if you think about this, the square root of 256 was 16. So that means 256 is a perfect square. Now, what happens when we have a perfect square here is we're going to end up with 2 real rational roots, and those roots will be integers when that happens. Since 256 is a perfect square, 16, what we ended up with here were 2 real rational roots. So if the value of the discriminant is a perfect square number, then the type of roots we're going to have are two real rational roots. And those two real rational roots, if you think about that, if you think about what the graph is going to look like, well, if our graph is crossing the x-axis at 14 and -2, and in this case, we know the a value was +1, isn't this one going to be going up, and then it's going to cross the x-axis? So those will be the two x-intercepts. So anytime you have a square number for the discriminant, you're going to have two possibilities for your graph. Now, I've drawn two coordinate systems here. One possibility is if the a value is positive, that means you know the parabola is going up, and you know that the parabola is going to cross the x-axis at your two roots. So your parabola is going to look something like that, or if your a value is negative, it might look something like that. Now, there's nothing to say that one of them has to have a negative x and one of them has to have a positive x for that. I just happen to draw them that way. As long as it's going up and crossing 2 points, or going down and crossing 2 points on the x-axis, that is still two real rational roots. And that happens whenever you have a perfect square discriminant. The next case is this one. Well, when we had this situation, let's talk about what that discriminant looked like. B squared was 1156, and we subtract from that 4 times 1 times 289. And when we did that, we saw that 4 times 1 times 289 was 1156 as well. So the number underneath the discriminant there is going to be 0. When that happens, we said we have the negative b plus or minus 0. Well, negative b plus 0 is the same thing as negative b minus 0. So that's not going to change the roots. So when this happens and we have 0 underneath the radical, we have one real rational double root. It shows up twice. Why is it a double root? Because we know that the x squared, we have to have two answers or two roots to our equations, two solutions, two zeros. So when we do negative b plus 0 and negative b minus 0, we get the same thing twice. That's why it's called a double root. So if the value of the discriminant is 0, then we have one real rational double root, because it shows up twice. The graph of that, now the graph of this is very different. It's still a parabola, it still goes up or goes down, but when you have a double root, what that means is your vertex is actually on the x-axis. So here the root is 17. What that means is A was positive, so I know it's going up, and it's crossing at 17. So that graph is going to be a parabola where the vertex hits on the x-axis. Your vertex is actually on the x-axis. If my A value had been a negative, well then that just flips it upside down and my vertex would be on the x-axis. Now, we won't know whether the vertex is on a positive or a negative number. That's going to depend on what we end up with as our final answer. It could even be a fraction, but the big thing here that you need to understand is if you have a double root, even if you have a double root in a polynomial function with a higher degree or a higher power, you're somewhere going to have that double root cross the x-axis at that specific spot. For the next one, if I find the discriminant, the square root of b squared, let's see, b squared is 16 minus 4 times 2 times negative 5. When I do that one, I end up with 16 plus 40. Well, 16 plus 40 is 56. The discriminant here is 56. Well, if you look at that, it's not a perfect square. It's not 0, but it is positive. Okay? So when we have the discriminant is a positive non-square number, in other words, it's not a perfect square, then you have, look at our roots, 2 roots still, because we have -2 plus or minus the square root of 14. So -2 plus or minus the square root of 14, well, square root of 14 is an irrational number. So we have -2 plus square root of 14 over 2 and -2 minus square root of 14 over 2, 2 real irrational roots. So what that means is they're just going to be crossing the x-axis at decimals. We won't be able to graph that very accurately. It's going to be a decimal. We will be able to tell what 2 numbers, what 2 whole numbers they are between, but that's about all we can do there. So when we have a positive non-square number as our discriminant, the type of roots are 2 real irrational roots. The graph of that looks very similar actually to this. I could say that those graphs are the same. The only difference is these are usually going to be a little bit easier to graph because they're going to be a nice whole number or a nice simple fraction usually. So for this one, our graph, and depending on whether A, in this case A was positive, our graph can be going up or our graph can be going down. And again, there's nothing to say that it has to be one positive and one negative root. As long as it's going up, hitting the root or hitting the x-axis in 2 places, or down, hitting the axis in 2 places, we have 2 real irrational roots. And then in the last situation, with this one, if we're looking for the discriminant, b squared is 36 minus 4 times a, which is 1, times c, which is 10, we ended up with 36 minus 40, or a -4 underneath the radical. Now we've talked about having a negative underneath the radical. When we have that, it's an imaginary number. We have to take the I out. So if you look at the 2 roots there, our 2 roots, we had 2 complex roots, or 2 imaginary roots. So when the value of the discriminant is a negative number, then the type and number of roots, we have 2 complex roots. Now, this graph is important. If you have 2 imaginary roots in your graph, what that means is, and this holds true for even polynomial functions that have a higher degree than 2, we don't know where these roots are because they're imaginary. Over here, this root was -3 plus or minus I. We don't know what number that is. It's imaginary. We can only imagine what it looks like, okay? So in my graph, what's going to happen here is my curve or my vertex never curves in such a way that it touches the x-axis anywhere. So now, if you look at this one, it had a positive a value, so I know this one's going up. So it's going to be going in an upward direction, and my vertex has to be above the x-axis because it never actually crosses the x-axis. It's imaginary. We don't know where it is. If my a value had been negative, all I know is that the vertex is somewhere below the x-axis and that it curves down when a is negative. So that's really all we can tell, but this becomes very significant when we're dealing with functions and we're looking at a function and trying to decide what type of roots that function might have. And that's true, all of these graphs hold true for any polynomial function. So if you have a double root, the vertex of, or one of those curves of that polynomial function will be crossing or touching the x-axis in one spot. That's where the curve is. If you have rational roots, like 2 rational roots, then it's going to cross the x-axis at 2 different spots. It could be like that or like this. And then if you have imaginary roots, they won't cross the x-axis at all. That curve happens either above or below the graph. So here I have 4 examples, and all they're asking us to do is find the value of the discriminant, then state the number and type of roots. So all you have to do is worry about the square root of b squared minus 4ac. All you have to do is find b squared minus 4ac and analyze what you would be getting underneath that root. So with this one, and remember, we have to have it equal to 0, okay? So I could just set this equal to 0. And then I have my a, b, and c. So my b squared would be 144 minus 4 times a, which is 9, times c, which is 4. When I do that math, 4 times 9 times 4 is 144. So we have 144 minus 144, or 0 underneath the radical. So the discriminant is 0. When our discriminant is 0, we know we have. In the next one, again, we have to get it equal to 0. So I'm going to have to move that 1 over. So that forces my c to be a -1. Remember, if you don't move that over, that's going to mess you up. So you have to make sure you're doing that very carefully. And then we find the discriminant. So b squared is 64 minus 4 times a, which is -5, times c, which is -1. -4 times -5 is +20, times -1 is -20. So we have 64 minus 20, which is 44. So it's a positive number underneath the radical. So that means we're going to have 2 real rational roots. It's already set equal to 0, so that's a little bit easier. B squared, 16 squared is 256 minus 4 times a times c. And so we end up with 256 minus 264. So when we subtract those, we end up with a -8 underneath the radical. If we have a negative underneath the radical, that just means that we have 2 complex roots. In this one, I have to get the 20x to the other side because remember it has to equal 0. Here I put that 20x in the middle because that's actually my b term. You have to make sure you have those in descending order to understand what a, b, and c are. And then for this one, b squared is 400 minus 4 times a times c. So we have 400 minus 400, which is 0. So again, that's the situation again. And remember, if you end up with the discriminant being a perfect square, you would have 2 real rational roots.